In this recording, Chapter 11, Part 3, we're going to talk about memory cells and antibodies. We're going to talk about their roles in secondary immune responses, and then we'll more specifically address the antibodies of the immune system. In humoral immunity, a primary immune response develops when the body first encounters the antigen. The antigen presenting cells present the antigen to the lymphocyte to initiate the immune response. And the primary immune response takes 1 to 2 weeks, but detectable antibodies will continue to rise for several more weeks, even though the infection has resolved. So we're showing the antigen is seen by the B cell. The B cells are activated, and that takes 2 to 4 weeks. Generally, within 10 to 17 days, symptoms will begin, and the B cells and the T cells begin proliferating and differentiating into the types of B cells that we've been talking about. Some B cells participate in phagocytosis, some become plasma cells, and some become memory B cells. The memory phase, or the secondary response, happens much more quickly because the memory cells are in the lymphatic tissue and they can more rapidly respond to future invasions. So when we have a vaccination, what we're getting is a primary response, the creation of plasma cells and memory cells, so that if our bodies see the invader a second time, the response is much faster and has a much greater magnitude because the lymphatic cells are already the B cells or memory cells are already in the lymphatic tissues. In this presentation, I've mentioned antibodies several times, and antibodies are proteins that are made by the immune system, and they're present in serum and in immune cells. They're also known as immunoglobulins. This slide lists the types of immunoglobulins and where they are found and their roles. You'll want to learn the immunoglobulins for the exam and for your future practice. IgM, and this little picture shows you IgM, it is the largest antibody, and its shape makes it ideal for pulling antigens together into clumps. This is the antibody that's formed against A and B blood types. IgG is the smallest, but also the most abundant antibody. The cool thing about IgG is that it does cross blood vessels and enters the placenta. So in this situation, if an Rh negative mom and an Rh positive dad produce an Rh positive fetus, then that baby's blood can leak into mom's blood and set up an antibody response. Mom will produce IgG, and that circulating IgG in her system could become a problem for future embryo. The IgA antibodies hang out in our noses, our bronchi, our digestive tract, eyes, ears, vagina, basically any spot with the potential to be exposed to outside foreign substances. IgA protect us from antigens that could enter. IgD is found primarily on the cell membranes of B cells, where it functions as a receptor, and it may play a role in B cell differentiation. IgE is found on mast cells and is a primary antibody in the allergic response. Now, I remember the names of the antibodies as God made, so God made all of them. And so it's IgG, IgM, IgA, IgD, and IgE. The antibodies are structured with some tips, and these tips on the antibody vary. And these allow us to have antibodies with very, very diverse sets of receptors. If the antibody ends up binding to a self-antigen, then the B cell cannot survive. Antibodies are important to immunity. They activate B cells. They trigger phagocytosis through opsonization. They also trigger the allergic response when they are inserted into mast cells, and that happens under certain allergies. Antibodies can also activate complement, and they can help take care of bacterial toxins by inactivating them or causing clumping. The complement system is part of the immune response, and it's triggered either by pathogens directly or by the antibodies. Ultimately, complement functions by perforating the cell membrane to make the pathogen easier for our immune system to destroy. Sometimes a cell will stop expressing MHC. The natural killer cells are part of the innate system, and they recognize these cells as malfunctioning and they kill them. The natural killer cells are important to cells infected by virus, but also to cells with altered DNA that could go on to become cancer or tumor cells. There are a couple of other types of antibodies that I want to mention here. Antibodies are being used more and more for treatment. So polyclonal antibodies have the advantage of being able to bind to several different epitopes, and they are generated by injecting an animal with a specific antigen to elicit a primary immune response. Then the antibodies can be harvested, purified, and administered to manage lots of diseases. So in pharmacology, monoclonal antibodies specific for one epitope are called MABs or MOBs, M-A-B-S. And the monoclonal antibodies, there's lots of different diseases that incorporate monoclonal antibodies. And polyclonal antibodies are being developed and are kind of are newer, of course. You do need to know the difference between active immunity and passive immunity. In active immunity, our lymphocytes are exposed to the antigen and we make our own antibodies. For example, if you get a flu shot and it stimulates you to produce antibodies to influenza, that would be passive active because you are making the antibody. However, in passive immunity, we're going to receive antibodies that were made somewhere else. For example, infants will receive passive immunity through the placenta and through mother's milk. Also, sometimes people could be exposed to a pathogen, such as hepatitis B, and post-exposure, people can be given hepatitis B immunoglobulins, and those provide them immediate passive immunity. They have to be given right after the exposure in order to be effective. But again, those hepatitis immunoglobulins were made somewhere else and given to people. It's a different a drug, basically, another pharmacologic. Neonates have very immature immune systems, but they are protected against antigens early in life as a result of passive transfer of maternal IgG antibodies through the placenta, and then they can get some IgA antibodies in colostrum and breast milk. In the elderly are at higher risk for diseases associated with the immune system. The aging immune system seems less able to recognize self-antigens compared to foreign, and this makes autoimmune diseases more prevalent as people age. Also, the macrophages tend to be slower to respond to invaders, and slower to respond to cells with altered DNA. And this may also explain why cancers are more prevalent in older people. The thymus begins shrinking during puberty and continues to shrink throughout the lifespan. So the number of T cells that are produced will be decrease as we age. And also another factor associated with aging seems to be that the CD4 cells don't perform as well in an elderly person. They decline in the production of interleukins, so they're not as good at signaling to make more lymphocytes come to the sites of inflammation. And also actual B cell function, the actual function itself tends to decrease with age. And that concludes our recordings for Chapter 11, Innate and Adaptive Immunity.